Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do Axis Symmetry problem. Now this particular topic was pending from our side from long time, and today what you see on my screen is a modeling of a Brinell hardness test, where actually you have circular workpiece. Over that you put an indenter, and based on deformed shape you calculate the hardness of the material. Now really we are not here to interested to measure the hardness of material, but the major motive from this video is to empower Abaqus user with this wonderful element called the Axis Symmetry element, and that power of that Axis Symmetry element, where you can really convert a 3D problem into 2D problem, and you can quickly solve it, reduce computational time, and still your results are quite closer to the reality. So right now on my screen you see the 2D things. You can also make it 3D, so I just make it 180, so you can see within 180 how the indenter is spacing the material. Now you also learn how to do contact. Now we don't want to do a simple problem where just applying pressure to the pressure vessel or anything. We want to empower the Abaqus user with how you can model a contact also here. So contact will be similar like 3D contact, but it will be a bit tricky. So this is exactly problem we are going to do. So before going into problem, doing a problem, we'll have a quick problem definition. Before that, I'll just tell you one thing recommended, but in case you know, then you don't have to go there. We have one video on a 2D continuum element overview and practical use to solve the 3D-dimensional real world problem. So if you are not aware of a 2D continuum element, we'll recommend you to go through this video, so you'll get an idea. It is just a 8.5 minute video. You'll get idea which 2D continuum element are there within Abaqus and where to use it. And then we have two videos on the plane strain and the plane stress. Again, they are two different videos. But highly recommended in case you don't know what is a 2D continuum element, you should go through this, so this will give a better idea. Now we'll quickly go to the problem definition. So we are going to do a Axis Symmetry modeling in Abaqus standard. This will be a quasi-static problem, so it's so slow application of force. There is no dynamic forces involved, so it is a static analysis. That's what actually we are going to do. We are going to model Brinell hardness test. So before going into detail, just quickly touch base with the different element type. Within Abaqus you have three different 2D continuum element. You have a plane strain element. Plane strain means if your third dimension is very high, then the strain in third dimension will be a constant, like a long pipe or dam or anything where third dimension is so large, your strain in third dimension is a constant, so you can use a plane strain element. If you have very thin structure like a rotating floppy disk or thin disk, where within in plane loading the strain in the third stress in the third direction is a constant, so you can use a plane stress. And then you have Axis Symmetry problem where you have anything is in circular shape. So you have a circular section, then you can 360 revolve, then you can use Axis Symmetry element, which is called CAX4. So we also have videos on the plane strain and plane strain. In case you want, you can have a look. We also the earlier video I recommended, you can go through that. We are going to model a circular workpiece. This will be like a 50 millimeter diameter, 10 millimeter depth. Then we have a 10 millimeter diameter indenter. We are going to give a vertical displacement 1 millimeter. You can use force or anything, but we are no more interested to really measure hardness. We are just using Axis Symmetry modeling. That is our whole purpose. Material, we are taking a brass soft material like 100 MPa 100 GPa modulus. So 100K is the MPa modulus. Plasticity, we are going to put 110 is with the plastic data for 0 yield, and 300 as 80%. It is like very ductile material, and then unit you are going to use ton, millimeter, Newton second. In case you get any different properties, steel or brass or bronze, anything different, you can use whatever convenient for you. And just just touch with this Brinell hardness stage, they applied force, and then this deformed diameter and then original diameter, they calculate what is the Brinell hardness number. So we are going to do that, so let's quickly start it. So I'm going to start. So let me set the directory. So let me first create a workpiece. So I say workpiece, it will be Axis Symmetry, deformable, shell, 200 is fine. Now I'll just quickly put point 0, 0. Now whenever you do any Axis Symmetry problem, whatever you are going to do, you have to do it in a first quadrant. That is a rule with Abaqus, so you have to do in a first quadrant. In case you tried modeling here, it will not take it. You have to do everything in first coordinate. First quadrant means your x should be the positive and y should be positive. X can be 0 also. It cannot be in the second, third or fourth quadrant. You have to do everything modeling in the first quadrant. So we'll quickly model it as 25, 0. So you get another point 25, 10, 0, 10. So 0, 10. So we are done. So our workpiece is ready. Now quickly go to the property. We are going to create brass. We don't require density or anything. We are going to use a static analysis. So 100 e power 03, 0.34 is this. Plasticity we are going to put 110, then 0, 300, and then around 80% elongation. We have done that. Now this is important. When you define one minute, something gone wrong. So once we define a section, you have to workpiece section. Now it is Axis Symmetry. You have to select it solid. So you say solid, and then that's it. For plane stress or plane strain, you have to click on this option, but since this is Axis Symmetry, you don't have to click on this option. So we have done this, and then you just assign it to this to workpiece. So we are done with this. We are done with workpiece. Now we'll quickly create indenter. It will be discrete rigid wire. Zero, 0, then you have 0, 0, 10, 0, 15, 0, 20. So radius is 5. So this is 10, this is 15, and this is 20. So I'm going to use this option, center point. This will be my first point, second point. That's it. So I'm done with this. Since the rigid part is ready, I'll quickly go to the property and assign him the reference point, because I'm going to give boundary condition on reference point. So we are done with reference point. So we created two parts. One part was rigid, one part was deformable. We are given material, section, everything. Now let's create quickly a instant. So we done the instant. Now we'll do couple of things. We'll again go to the part, and then workpiece. We'll first create a slave surface. So I select a top, done. Now for workpiece there is no issue, but whenever you create for master for like line rigid surface, this will be tricky. So this will be the important learning. So once you select this, it will ask for the two choose a side for edge. Now most of the time people get confused. This magenta and yellow, people think that this is the outward normal, inward outward normal. It is not. So yellow is you want to create on the outer surface. Magenta is whenever you want to do on the inner surface. So in this case we have to take it outer. In case you take a inner, your contact may not work. So select proper. So yellow outer we are selecting. We have done that. So two surface we are done because we want to define an interface between them. Now we'll first define interface and then we'll define other. Contact, we are going to use a friction value here. Penalty based friction, we are going to use 0.5. It's just a compression, so there is minimum sliding, so we are going to use a rigid surface versus deformable. So 0.5 as this. We'll create surface to surface standard contact. So master surface I am going to select indenter, and slave surface I am going to take workpiece, and here we are define this. So we are done with that. So interface we are defined. Now quickly we put a mesh. Let me first workpiece. So workpiece we are going to put very fine mesh 0.3. That's what actually we are going to put. Now we'll also, so standard library Axis Symmetry trace. So you see CX4R, that is what element it is selected. So once you say Axis Symmetry, it will select that CX4R, a 4-noded bilinear Axis Symmetry quadrilateral element. And then we select this. I also prefer to do a medial axis theorem, and then it just create quite a bit structural mesh for this. So it's a quite structural mesh. We'll go to indenter. Now for indenter also you see we are click it's by default it's selected RAX2. It is a 2-noded linear axis symmetry rigid link, so it is a planar axis symmetry rigid geometry. And then we are going to select again very fine 0.3, because it's a contact problem, you have to have quite a bit compatible mesh. And then we have created the mesh. So this is what it looks like exactly. So two meshes we have created. Now let's create a boundary condition. So workpiece boundary condition we are going to hold at the bottom. So now since it's axis symmetry problem, CAX4, it will have only 3 degrees of freedom. It's radial, theta and z, only 3 degrees of freedom. That's the reason it is a faster. So converting a 3D problem into 2D problem with just 3 degrees of freedom, you get similar result, but number of degrees has reduced, your computational cost has gone down. So that's what actually we are constraint r theta z. We quickly create a step. We'll say axis symmetry, NLGeom on. This is just a end time. Since there is no time involved, it is just a full load. 1 millimeter will apply at the 1. Initial time step will start with very minimum 1.01. We have done that. Now you might be thinking why I not applied a displacement 1 millimeter before the step, because this will be a prescribed displacement, so it should be inside the step. So again I'll go to the load. You'll create here BC2, which will be displacement, and this will be, we'll select that reference point, and then we'll say radial will be 0, theta will be 0, and this will be minus 1.0. so it will just move down. So we have done everything. So let me save this file. Let's create a job. let me write a file. So input file is written. Let me check a data check. Let's do a data check. So we have submitted for data check. So there is no issue. So pre-processor completed, everything is done. Let me check. Let's look into input file, how input file looks like. So I generally use the text pad. I also recommend a text pad is better. Notepad is also fine. So we'll put star. So node, then this rax2, it's a rigid element. Then you have set definition, and then you have node for part. CAX4 is a workpiece. Then you have assembly, you have surface generation, again some node set, rigid body, material definition. You have interaction property, friction details are there. You define the contact. We are given the step details, static nl is equal to yes. We are going to with 1% loading to start with. Then we have this. So you see 1 2 3. So it's xy theta or r z theta. So that's what actually 3 degree of freedom. So x, y and theta, and that's we are done. We are moving the workpiece by 1. So everything is fine. I'm going to run this from command prompt. I generally run from command prompt, but you want to run from, you can also run from submit a run from here. I prefer to so cd, I just copy the folder, then I say abq6145. that is what I have, 6.145. job is equal to, I'm going to copy that job name. I'm going to run with 2 CPU and interactive mode. So let's start the run. So it's just gone in standard. Let's look into how the results look like. So this was, I'll just take it. So you can see it just started. So it's pushing the workpiece. So we are almost 38% we are done. Still the run is going on. So let's wait for results. I think this is a quick run. It almost got to 80%. So we are done. So it's almost done. So let's have results. So you can see the one moisture stress, how it is pushing, and then you can measure plasticity and how much is this diameter, and you can do it. Now once you solve this problem like a 3D problem converted into 2D continuum problem, while post processing you always give results in 3D. So that also looks good when you represent this at, because a lot of effort who has developed these elements, the Axis Symmetry element, they have put to really solve our major pain. So how to get these 3D results? You go to ODB display and then sweep element. You can have 360. I'm just going to do with 180. So when you submit a results to customer or to show your friends or professor, you either do it 180 and then show it. So this is how it looks like. You can do different things. You can look into stress, you can look into displacement, you can also look into plasticity data, it's up to you. So thanks a lot for watching this, guys, and this is one of the pending thing from my side long time, is to empower Abaqus community with tutorial on the Axis Symmetry problem, which we are done today. So I guess you can go ahead and then do practice this Axis Symmetry element. You can solve your problem with Axis Symmetry element. And if you like this video, don't forget to like us and subscribe us. Thanks, bye bye.